Hi guys. So today I would like to talk about Asian options. Now Asian options are path dependent options where the payoff of the option depends on the average price that the stock has taken over certain time interval. Okay? So we could basically look at, if we have on the x-axis we have time, on the y-axis we have the value of the stock, and if this basically capital T corresponds to the expiration of the option, then the payoff of an Asian option could depend on the average value of the stock price over the entire time period from 0 to T. Or we could also look at, instead of looking at the average over the entire time period, you could also look at, let's say this basically is T minus C, so this is C. Okay, you could also look at just the average over this time interval. Okay, so depending on what kind of a payoff you basically put in a Asian option, you could look at the average over the entire time period, or you could look at a smaller time interval before expiration. So you could basically look at what is the average price from here till here. Okay, and depending on the average price, you would basically have a payoff. Now, in case of a stock price with continuous sampling, basically the average price that the stock basically takes between time 0 and t can be written as integral 0 to t s of t dt 1 by t, right? So if you basically consider continuous sampling, then the average stock price over 0 to t basically would be given by this integral. Okay, and we could then define a payoff of a Asian option. Okay, the payoff of the option at expiration can be then given by the average stock price 0 to t st dt minus some fixed strike price. Okay, and we need to take the maximum of this and 0. Okay, so this basically would be a payoff of a Asian option. Here we basically are assuming that the payoff depends on the average over time from the entire time period from 0 to t, but it need not necessarily, it need not be from 0 to t. You could just take the average. You could define a payoff where the average goes from t minus c for some constant c, okay, to t. So in that case, we would just consider the average value of the stock between or during this time interval. Okay, so in today's lecture, what I'm going to do is I'm going to consider this payoff for an Asian option, and as you can clearly see from this, basically the payoff basically depends on the path that the stock price basically takes. Okay, so if, for example, if the stock price had taken this path to reach the same S of capital T, then the payoff would be different because the average here would be different from the average here. So these options are basically path dependent options. Now Asian options don't really have a closed form solution, and basically what we're going to do in the lecture is we're going to look at the differential equation that is satisfied by the formula for a Asian option. Okay, and we already know the whole process, how we actually come up with a differential equation, a partial differential equation. What we need to do is you first need to express this payoff in terms of state processes. Okay, so the procedure of basically coming up with the differential equation is, first this payoff needs to be expressed as a function of state processes. Okay, function of state processes. Once you basically express this as a function of state processes, then we know that the value of the option is only defined by those state variables and nothing else. Okay, and then what we can do is we need to identify a martingale. Okay, and we know that the discounted value of a derivative security is a martingale. Then we need to take the differential take the differential of the Martingale, and because we're taking differential of a Martingale and Martingales don't have a dt term, set dt term to 0, right? And if we do that, we'll basically get our partial differential equation. So let's basically look at expressing how we can express this as a function of state processes. Okay, so we'll go through each step, and as we do that, we'll basically come up with a differential equation. So let's do that. Okay, so we want to first express the value of a Asian option as a function of state processes, and let's denote y of small t as integral 0 to t of s of u d of u. Okay, so this basically is the integral of the stock prices between time 0 to t. Okay, and that we're denoting by y of t. If we do that, then we can see from here dy of t can be given by s of t dt, and because it only has the dt term, dy times dy would be equal to 0, right? So this basically is y of t. Now what we want to do is we would like to basically express the value of our Asian option at time t as a function of time and state processes. Okay, and what I basically claim right now is basically this: if we take a vector of state processes given by s of t, which is the value of the stock at time t, and y of t, okay, this vector of state, this vector of processes basically together is a Markov. Okay, I'm not going to prove that, but you can actually look at the Markov property, and you can see that this basically is a Markov. Okay, and if you and if this is a Markov, then we can basically write this as a function of s of t and y of t. Okay, so what I'm basically trying to say here is the value of the Asian option at time t depends on the time. It basically depends on the value of the stock at that point in time, and it basically depends on this integral till time t. Okay, if we know these three, then we basically can compute the value of the Asian option, and it doesn't depend on anything else. Okay, and this basically comes from the Markov property of st and yt together. Okay, because intuitively you can see that if this was only a function of time and st, okay, if you only knew the time and the value of the stock at any point t, that would not be enough. Okay, because this is a path dependent option, and we need to basically have some information about the path that the stock has taken till that point in time. So just having these two variables does not suffice. We need to add this to make this a Markov, and that together would basically give us the value of a Asian option. Okay, so this is my first thing that I wanted to do. I wanted to basically express the value of a Asian option as a function of state processes, and I'm claiming that these two together basically constitute a Markov, and then we can write the value of the Asian option as a function of time st and yt. Okay, but yt is given by this integral. That's the first thing that we've done. Then the second thing we need to basically look at, identify a martingale. We know that the discounted value of a derivative security is a martingale under the risk neutral measure, right? So we can basically write Vt times e to the power of minus Rt is equal to expected value under the risk neutral measure of V of capital T minus Rt given information at time t. Okay, this basically is our risk neutral pricing formula. So from here we can see that discounted value of a derivative security is a martingale. Okay, and instead of Vt we can basically substitute Vt by this function. Okay, now what is the third thing we need to do? We need to basically take the differential. Okay, so if I basically substitute Vt here, we'll get e to the power of minus Rt, and instead of Vt I'm going to write a function of time st yt, right? And I now need to take the differential of this. Okay, when I take the differential of this, I'm taking the differential of martingale, and I'll get a dt and a dw term, and I just need to substitute the dt term equals to 0. Okay, which basically is my fourth step here, because when I take the differential of a martingale, it should not have a dt term. Okay, so let's take the differential, and equate the dt term to 0. Okay, so now we need to take differential of this, and before we take differential of this, just basically let's look at the cross variation, the quadratic variation, all of that stuff. So in our case, the stock is basically modeled as a geometric Brownian motion. So we know that ds of t is equal to r st dt plus sigma s of t dw tilde of t, right? So we know that ds of t is given by sigma square s square dt, right? And because dy of t is given, it does have a dt term, it doesn't have a dw term, so from here we can see dy is equal to 0, ds times dy would also be equal to 0, right? So using this, now we can basically look at what is the differential of this and group all the dt terms and set them to 0. So let's take the differential of this. If we take the differential of this, we'll get e to the power of minus rt minus r. Now I'm going to write just this function. I'm not going to put all the arguments there, okay? And we'll get dt. Then I'll get e to the power of minus rt, and I need to take the differential of this. Now, in order to take differential of this, this will be v of t dt plus v of s d of s. Okay, it's a function of three variables, time, s, and y. So vt, v of s plus v of y dy plus we're going to have dt term, which is going to be 0. We're going to have our dy term, which is going to be 0. We're going to have all these cross terms, which are going to be 0. So the only other term that's going to remain is half vss ds ds, right? So now we can basically solve this. Let's take e to the power of minus rt outside the brackets. We'll get minus rv dt, and we have v of t dt from here. Now instead of d of s, let's basically write down what d of s is. That's sigma s dt plus rs dt times sigma s dw tilde, right? That's ds plus v of y. Instead of dy, we basically have s of dt, so we can write s dt, right? And then finally half vss ds as I just said is sigma square s square dt. Now what we need to do is we need to group all the dt terms together. So we have a dt term here. So let's write this as e to the power of minus rt minus rv plus, we have a dt term here, v of t, taking care of this. Now we have dt term here, rs v of s, right? Then we have a dt term here, s times vy, right? And finally we have half vss sigma square s square times dt, and we'll be left with one dw term, which is sigma s v of s dw tilde, right? So that's what we're going to get. Now what we need to do is we just basically, because we are taking differential of Martingale, the dt term needs to go to 0. So if we substitute dt term equals to 0, we'll basically get vt plus rs v of s plus s times v of y plus half sigma square s square vss 1 2 3 and is equal to r of v. Okay, so this basically is the partial differential equation that we get for an Asian option, and now we need to basically look at the boundary conditions. Okay, so let's look at the boundary conditions now. Okay, so let's look at the boundary conditions. So as we said, v basically is a function of, it had an argument t, and basically the value of the stock and the integral, okay, the sum of the stock process over time interval 0 to t, which is given by a dummy variable y, okay. So this basically is a function of three variables t, s, and y, and the boundary condition that we want to look at first is when t equals to capital T, that means that at expiration, if the value of the stock is s and the sum of the stock process is y, then this basically is nothing but the payoff of the Asian option. And payoff of the Asian option, we know what it is. We need to take y, the average stock price, minus k plus. Okay, this just is the payoff of a Asian option at expiration. At expiration, the sum of the stock price was given by y, so we need to take the average y divided by capital T. That basically is the average stock price at expiration, minus k, which was the strike price, and we need to take the maximum of that and 0. Okay, so this just is the payoff of the Asian option. Now we also want to look at what happened if at any point in time t our stock goes to 0, okay, and if at time t the sum of the stock price till time t was equal to y. Okay, now if basically stock goes to 0 at time t, we know that because we are modeling the stock as a geometric Brownian motion, the stock will basically stay at 0. Okay, so whatever was the sum of the stock till that point in time would basically be the same sum that will remain till expiration, because all the other stock prices would be 0. Okay, in that case, what would be the payoff? The sum at expiration would be y, average would be y by t, okay, minus k would be the payoff at expiration, and we need to discount this. We need to discount this back to today, and we are starting at e to the minus r t minus t. Okay, so this basically would be my the value of my Asian option if the stock goes to 0. So this basically was the payoff at expiration. Because the stock has gone to 0, it will stay at 0. So whatever the sum we had at time t would be the sum at capital T. So that would be the sum. We need to take the average, so we need to divide by t minus k. This basically would give us the payoff at expiration, but we are standing at time t, so we need to discount it back. So this basically is the discounting. Okay, so this would be the other boundary condition. And finally, we want to look at a boundary condition if at any point in time t as y, if basically limit as y goes to minus infinity. Okay, what happens if this y basically goes to minus infinity? Then basically we have a boundary condition. So basically, if at time t the sum was s, okay, we could basically write this as, okay, so if at time t the sum of the stock process till that point in time was y, then we can write y of capital T, which is the sum of the stock process from 0 to capital T, as y, which was the sum from 0 to small t, plus the sum from t to capital T of s of u d of u, right? So this was the sum till time t, small t. So that I've written here. Then basically I need to add basically the sum from small t to capital T, and this together would give me y of t. Now if this y goes to minus infinity, this y of t would also go to minus infinity, right? This also goes to minus infinity, and since our payoff is given by this formula here, max of this and 0, okay, we are sure that the option is going to expire out of the money, okay, and hence we basically, what we'll get here is we'll get a 0, because this would be a negative quantity and we need to take this, the maximum of this and 0, which we'll get 0. Okay, so these basically are the three boundary conditions. This basically is just the payoff. This basically, I've already explained to you what the logic behind this is, and this basically comes from the fact that if y goes to minus infinity at small t, okay, then y of capital T also goes to minus infinity, and in that case this term inside would be negative, and we need to take maximum of negative quantity and 0, and we'll get 0. So we have basically, I've shown you the differential equation for an Asian option and the 3 boundary conditions. Okay, so hopefully this was clear. Quite simple actually. We've done this many times before. We need to basically first express the value of an Asian option as a function of state processes. Then we basically needed to identify a martingale, take the differential of the martingale, set the dt term equals to 0. When we did that, we basically got this differential equation with these boundary conditions, right? And hopefully that was clear. So let's move on.